I'm Veer Mahajan, and this is my semester 2 final project on eigenvalues and eigenvectors, a quick introduction from 5.1. So let's start with a very quick example, and not an example with numbers, but just kind of giving you an idea of what eigenvalues and eigenvectors are. So let's say we have a random matrix A, and we're multiplying it by some vector u right here. Right? It's a square matrix A, we're multiplying it by u, and the result that we get is just a scalar multiple of u. So of the same vector u, we're just getting a scalar multiple. So of course, lambda here is a scalar, A over here is a matrix. And over here, in this particular example, what we've basically gotten is a transformation of the vector that's basically just a linear multiple, a scalar multiple of that, right? And over here, we actually have an eigenvalue. This is going to be the eigenvalue. And this u over here is going to be the eigenvector, right? Now, what is the use of this? Well, these can be very, very useful to us in all sorts of contexts with matrices. Sometimes it can help us in finding the determinant. Other times it can help us in determining invertibility. A lot of times when you have these values, you can actually diagonalize a matrix, and that allows you to find powers very, very easily. And I don't want to get into all of that right now because those come up in subsequent sections. But the point is there are lots of different applications. And over here, we're going to kind of look at how we can take this very basic definition and turn it into a surefire way of finding both the eigenvalues and the eigenvectors, and then we'll do a few practice questions. So let's take this exact same equation, right? We've got vectors on both sides, so let's just subtract the right hand side from the left hand side. So we get a times u minus lambda u, and this is just going to equal 0. Multiplying lambda u by the identity matrix won't change anything, right? That's the definition of the identity matrix. And so we can just do it like this instead. We just throw in the identity matrix over there. And we're omitting dimensions here, but of course, these will have to have the same dimensionality, right? So you can subtract them. So that sort of stuff is just given. We're abstracting that away. And over here now, you can actually factor it out. So we get a minus lambda I. And if you've seen the form before, you'll see that it's already getting quite similar. This is equal to u. Now, we want different eigenvectors, right? We want to satisfy it for not just, okay, to make this work, you either need this to be 0, right? Or you need this to be 0, or you need the product of them to be 0 in some other way. And for this to be 0, you need lambda to equal a, but obviously that won't work, right? Unless a is itself, unless a is a scalar multiple of the identity matrix, and then lambda is that scalar multiple, you won't get this being 0. So the point is, we don't want u to just be 0, right? That's too simple. That's a trivial solution. And so instead, if we want multiple different solutions for this, we want the determinant of this matrix, right? And this is just from the previous section of determinants that we learned as well. The determinant of this matrix should be equal to 0, right? That's the conclusion that we get just considering this definition over here. We don't want this to be 0 because then they're not different eigenvectors. All the eigenvectors will just be the 0 vector. That doesn't work. And so we basically say we want the determinant of this to be 0. Writing that a little more succinctly, what are we going to get? We're just going to get the determinant of literally just what I said. A minus lambda I is equal to 0. And this over here is known as a characteristic equation. And this is actually the definition that we're going to use now to actually find the values, right? So let's just dive right into an example, right? Let's say we want to determine the eigenvalues of this. After we find the eigenvalues, I'll go back up here, we'll look at the theory, and we'll see how we can get the eigenvectors. But let's just start with this, right? So we want to find the eigenvalues of this. Okay, so what do? Well, we want the determinant of this minus lambda I. So A is equal to this big matrix over here, 1, 0, 4, 0, 4, 0. Just bear with me, maybe take out paper, pencil, or whatever, and do this yourself as well. And I'm going to skip a step here. We're doing lambda times I. So that's just going to give us lambda, 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 0, 0, 0. Right? You could have written it out, but it just saves some time like this. So it's going to be a little bit messy, but it's not that bad. We get 1 minus lambda, then here we have 0, then here we have 4. Here's 0, we have 4 minus lambda, 0 again. Sorry, not 0. This is going to be 3, this is going to be 5, and negative 3 minus lambda. Right, and we want its determinant to be 0. So I'm actually going to go ahead and just erase this stuff and change it to the determinant like this, right? That's it. Remember, lines with the things at the bottom and like vertical lines are different things. One is just for a matrix, one is for a determinant specifically. And now what do we do here? Well, it's definitely not, the prettiest matrix, but we can probably do something with it here. So we can take this row, start over here, right? We can start with that because these two are both zeros. It makes our work a little bit easier. So we have 4 minus lambda times the determinant of 1 minus lambda, 4, 3, and then negative 3 minus lambda. What is the determinant of this going to be? Well, we keep the 4 minus lambda. That doesn't go anywhere. And then over here we have the product of these. So that we can write that as lambda plus 3 times lambda minus 1. Hopefully you see why. And then minus 12. Okay, let's simplify this a little. So we still have 4 minus lambda times, what do we have here? Well, we'll have lambda squared plus 2 lambda minus 3 minus 12, so minus 15, which is just equal to, so keep the 4 minus lambda again. That's not going to go anywhere. Remember, don't forget that. And then this is lambda plus 5, lambda minus 3. This is now lambda minus 3, not equals 3, although that is also true. And now we can finally equate this to 0. What do we get? We get lambda 1 equals 4. Lambda 2, order doesn't matter, by the way. I'm just like naming them like this so it's clear what's going on. And there are 3 different values, right? If you plug any of these in and then evaluate the determinant, you will get 0 as well. So that's just a little check that you can run. And we're done. So we found the eigenvalues. That's all the question was asking for. Now let's think about what happens when you want to find the eigenvectors, right? What are the eigenvectors going to give you? Well, think about it. We've plugged in our lambda over here and we've gotten this. Now we want to find u, right? What u works for this? Well, that's nothing but the null space, right? If we've got a matrix times, we've got some matrix a minus lambda I times some vector u equals 0. So the u values, the possible vectors that you can put in for u are the null space, right? Or belong to the null space. So that's, now we have to plug these values in and then we get the null space. So let's do that. We denote them as such. So it'd be like E1, right? Like okay, wait, like this. Well, okay, so there are different ways to do it. I think the easiest way, just so that you know what you're doing, right? In case you don't put the order, you just write the eigenvalue that you're putting in. So over here, I'm going to put in the eigenvalue 4. And so when I plug this in as lambda, we're going to get 104,040,353 minus 4 times the entry matrix, right? So that's going to be negative 3, 1, negative 7. And then everything else is the same. 040035. Zero zero 35, is that it? Let me just check. 35, yeah, that looks about right. And now we need to find the null space of this, right? So let's quickly do that. Doing a few row operations here. Sorry, I had a sneeze there. But yeah, we can just add them up. So we get 5 over here. So 0, 5, and negative 3. And then we have, well, no, that should actually go here. 0, 1, 0. And so what do we have here? We have, that should not be a 0, sorry. I'm trying to go a little fast and not show all the work necessarily because we've done that in the past already for enough other things. I'll just go 3, 0, negative 4. All right. Now, if you want this to be equal to 0, right? So we're just basically going to be doing this. What does that tell us? Well, now we can go all the way to RRDF and we should, but just for the sake of the video, because of the limited time that we have, I'm not going to do that. That's the only reason. Otherwise, I should, you should, everyone should do that. We know that x2 is equal to 0. The pen is really bad, but sorry about that. Which means x3 is equal to 0. Right? And if that's the case, wait, is that correct? Let me just check actually. Yeah, none of these are actually going to be free. There are no free variables over here. Wait, I don't know if I did it correctly actually. Oh, sorry. This should be 0. Okay, that explains it. So this would then be 0, and then we can't say that. Okay, my bad. Sorry about that. Just ignore that. But yeah, now let's see what we have here. We can just say that x1 is equal to 4/3 x3, can't we? What's the free variable here? It's obviously x3, right? Then we can similarly say that x2 equals 3/5 x3, x3 equals x3, and so this is our answer: 4/3, 3/5, and 1. We can multiply by 15, right? Because um, yeah, I mean, there are enough things you can do. We can multiply by 15 and take it out as a scalar, but the point is that this is going to be an eigenvector. If this is going to be an eigenvector, you can also have any linear multiple of this, and that would also work, right? So now we found that for E4. Now let's go on to the next one, E3. Let's just go with that, right? And the point is that you keep doing this, right? And so we, just to be clear, this lambda value, so that's lambda 1 equals 4, this corresponds to this, right? And that's why we denote it this way. With E3, it will now be -2, 1, -6, -2, 1, -6. I think this is 0, this is 0. I think this was also 0. This was a 3 and a 5, if I remember correctly, and then that was a 4. All right. What do we do here? Well, okay, we can do, if we multiply this by 3 halves, we're going to get 3 and 6, and then we add this to this, and those cancel out. So essentially, we have -2, 0, 4. Then we have 0, 1, 0. The bottom one becomes 0, 5, 0, but that cancels out, so that goes away as well. And so that tells us x2 is 0. It has to be. And then x1, so we have x1 equals 2x3. And so this gives us a final answer of 2, 0, 1. Right? I went a little bit faster over here. Sorry about that, but I'm just trying to, save some time. Lambda, so e sub -5. Let's try this one now. It's going to be a little longer, but that's fine. Well, it's not going to be longer, but it'll just be a little messier maybe. 9 and 2, 3, 5, 0, 4, 0, 0. Okay, I mean, same idea. We can like just directly see that this will cancel when we multiply this by half. So we have a 604 on top, and then this will cancel out as well. So x2 is again going to be 0, and then we just have -2/3, 0, 1. Reason for this is that 6x1 equals -4x3, right? So I did that a little faster in my head, but that's the idea. So now we've got all the eigenvalues, 3 of them, and all the eigenvectors. It's very messy, definitely, because it's a long question, right? But we're done finally, and that's kind of how it works. Now, there's very little theory over here, but it's very meaningful stuff, right? So try to keep this in mind. I don't think there's too much more to share in this video. We can do a quick example with 2, I guess. So yeah, with a 2 by 2 matrix. So let's do that very quickly, just so you can get a little bit more practice. What would we do over here? Well, we'd first take it to 2 minus lambda. This would be 0, this would be 1, this would be 3 minus lambda. What I like to do when I'm dealing with a 2 by 2 matrix is, just so that everything looks a little nicer, since I'm multiplying these two and then negative, negative, I just do lambda minus 2 times lambda minus 3 minus 1 equals 0. Just because the lambda squared, it's positive and it's easier for me like that. This would just give us lambda squared minus 5 lambda plus 6 minus 1, so plus 5 equals 0. Does that seem right? Yeah, I guess so. Yep. Oh no, sorry. This is 0, so it's minus 0, and then this would be plus 6. So obviously, just from here, we know that lambda equals 2 and 3. Right, and actually this, oh, okay, well, if I'm on this topic, 2 and 3, right, this looks pretty easy, like, oh, we got 2 and 3, those just happen to be the diagonal elements. And in general, this is actually true for any block matrix, and this is kind of where the fun begins with eigenvalues. So if I have something like this, looks pretty nasty, right? Like, oh, it's a big matrix, how am I going to do this? Especially if I start putting in random numbers here like this. how do you find the eigenvalues, right? Find eigenvalues. You might be tempted to, use a calculator or just give up on the question altogether. But remember, how are the eigenvalues defined? You just want the determinant to be equal to 0. This is a not a diagonal matrix. It's a block matrix, right? Because you've got this entire block filled with zeros. I think it's an upper block matrix. And so the determinant is actually just the product of the diagonal elements. So it's going to be 1 minus lambda times 2 minus lambda, 3 minus lambda, 4, well, I'll just write it out, why am I skipping that? 3 minus lambda, 4 minus lambda. And so what are our lambda values going to be? What are our eigenvalues going to be? They're obviously just going to be 1, 2, 3, and 4. This works. Let's do one more thing, because we're running out of time. I don't want to go too deep into all these concepts, but just kind of a teaser for the next few lessons as well. We've understood this. Now, what if we had something like this? Still an upper triangular, an upper block matrix. I'll give you some random numbers here. What do we do here? Well, we're going to have this time not 3 but 2 unique eigenvalues, right? Because we just take the diagonal elements. So we have lambda equals 1, 1, and 2. And this might remind you of something where, like in algebra, when we were dealing with multiple roots, right? And repeated roots, oftentimes you'll get, you could just have x minus 1 whole square equals 0. And the duplicity is called 2. Not duplicity, that's an English word. Multiplicity is called 2, right? Over here, we actually have two things. We have the algebraic multiplicity, which would be 2 for lambda. But when you actually go ahead and plug lambda in, and you find the eigenvectors over there, you'll get, so remember, there are infinitely many eigenvectors. If the dimension of the space of the eigenvectors you have is 1, then the geometric multiplicity is going to be 1. And if the dimension is 2, then the geometric multiplicity is 2, and so on, right? And there are important rules over there that arise as well, but I'm just giving you a teaser so that, you've learned how to find the lambda values, you've learned how to find the eigenvalues, eigenvectors, and all that. But just giving you a little teaser, going beyond the theory into some actual applications. I'll leave you with one last thing, right? So I just wanted to show you that, yeah, there are some tricks sometimes. I just wanted to give you one last example. Oftentimes you can write a matrix in this form, right? This is called diagonalizability, and this is definitely not content to be covered in this video, but I just wanted to give you a little teaser again, right? And let's say we want to do a squared. So then that would just be this times this, right? But what does this become? Well, this and this are going to cancel out, giving you I, and so we get PD squared P inverse. Now, what if we do this again? Let's do a cubed. We're going to get PD squared P inverse, PD P inverse. Again, these cancel out and give us I, and now we just get P D cubed P inverse. And so if you continue this logic, eventually we're going to get A to the n is just equal to P D to the n P minus 1. Now, what does this D stand for? It's a diagonal matrix. It's something like this. Okay? And so taking this to some power is going to be very easy, because this is just equal to 1 to the n, 1 to the n, 2 to the n, 0, 0, 0, 0, 0, 0, 0. It works in this specific case, but the point is the power of diagonalizability also comes from eigenvalues. In fact, these elements here, they're lambda 1, lambda 2, lambda 3, right? And then these over here are actually from the basis of the eigenspace with all the different eigenvectors that come up. And so sometimes, remember, the basis has 2 eigenvectors, and then P inverse is obviously the inverse of that. So the point is, eigenvectors and eigenvalues and eigenvectors are incredibly powerful. We've only just started scratching the surface on how you kind of discovered how the theory connects to the formula, how the formula shows you how to find them. But there's a lot more. There are all these sorts of tricks, like with diagonal matrices, and then there are these sorts of very powerful manipulations that can save you so much time. Because if you have an ugly matrix and you multiply it by itself again and again and again, that's like 5 times. That's so much more work than just diagonalizing it instead and then doing this, right? So I just wanted to share those insights. But at the end of the day, this was mainly just supposed to be a video focusing on eigenvalues and eigenvectors. So thanks so much for watching. Hope you enjoyed. And that's it. Bye bye.